The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
And the next speaker is Kamal Kayat. I guess most of you guys know him. But anyway, he is a professor in civil engineering and director of the Center for Infrastructure Engineering Studies at Missouri University of Science and Technology in Rolla. He is a fellow of the American Concrete Institute and serves on several technical committees, including being the chairman of ACI 237 on self-consolidating concrete. And he's also chairman of the RILAM Technical Committee 228 on mechanical properties of SCC. Please come out. Welcome.
Thank you very much, Peter. Ladies and gentlemen, like Peter presented me, recently I moved from University of Sherbrooke in Quebec to University of Missouri Science and Technology in Rolla. But I still have all my research activities still there, and what I'm at Sherbrooke. And all the students that are still there are very active. The work I'm going to present to you actually was done at Sherbrooke within the industrial chair that I'll describe in a minute, but the work was done to evaluate the robustness of SCC subject to variations of sand humidity and superplasticizer dosage. And I'll tell you a little bit later about the type of concrete we were targeting, but as you can see from the picture, obviously over here, we're very concerned about precast, pre-stress applications. Alright, like I said, this work was done at Sherbrooke during that time period over here. This is an ongoing study on high-performance flowable concrete with adapted rheology. So this is a new class of high-performance concrete where rheology comes into play in terms of optimizing the performance. It's an insert which is equivalent to what we have in the States National Science Foundation. So this is the equivalent in Canada insert chair involving 17 industrial partners representing basically all the chain that leads to development and acceptance and implementation of the technology. So this is very, very powerful tool to get technologies out there within 5 years into users. And so the work I'm presenting over here, forgot to present my co-authors, Siwar Naji, which was working on her master's during this period. What I'm presenting, Sudok Wang, was also working on his postdoc. So the way we define robustness is robustness of concrete is defined as the capacity of that material to tolerate certain variations in material characteristics and mixture parameters. I think Nicola came in late, but I'm sure that he spoke about this as well. So if you look at the zone of opportunity, for example, if you say my concrete should have a minimum slump flow of say 600 and maximum slump flow of 750, for example, that defines filling ability. And a concrete that is robust is a concrete which will give you, within the variations of a parameter, let's call water cement ratio, will give you a lot of ability to vary that and still meet that criteria. So this is what I would call a robust mix versus a very narrow window of opportunity where the water cement ratio has to be controlled very, very much so to be able to meet those criteria. So a robust concrete has lower sensitivity to variations in the mixture parameters, but also in the mixture constituents and the mixing parameters, which are the temperatures, the mixing time, And as we saw from Dr. Russell's presentation, the water cement ratio, or the amount of water that you can add, the limits of plus or minus 10 liters per cubic meter, is really the most important parameter, and this is why we studied in this evaluation the effect of the sand moisture content by changing the water cement ratio of the mix, and also to a lesser degree the variation of superplasticizer. And those are parameters that are very important to producing on daily basis a stable and consistent production of SCC. So the objective of our study was threefold. One of them was to evaluate a combination of different superplasticizer viscosity enhancing agents on the robustness of SCC subjected to variation in sand humidity and super dosage. But also was to propose a methodology to evaluate robustness. How do you evaluate robustness? We saw one approach in the previous presentation, which is a very good approach using rheology, and also to define test methods that would be suitable or sufficient, let's say, to enable us to evaluate the robustness. So if I'm presented with a mixed design or a type of binder or aggregate admixtures, do I need to do all the fresh and mechanical properties and durability, or can I, from a statistical point of view, say, okay, I can zoom on a few tests to be able to do that exercise? So for the first part of the study, which is the main part of my presentation, is we're looking at different type of viscosity enhancing agents. In the industrial chair, we have many chemical admixture companies, and we looked at different VMAs. So 5 of them, I'm calling them over here, polysaccharide 1, polysaccharide 2. Both of them are dietine gum, but that they have different maximum diameter. So the one that is here, the PS1 is coarser than PS2. So this is a finer grind. And then we have a Wayland gum, which is PS3. That is the coarse one. And then we have a cellulose product, and I'm sure Nicola will ask me which one it was. So it's the HPMC. At maximum also 212, so a coarse grind. And then we have the modified starch. Now, the reason that those were selected, and by the way, these are not formulated products, so our admixture companies that are our industrial partners did not furnish those products. These are the products, if you would, that are used to formulate some of their admixtures, and there's other things in them, of course. So these are the I would say the base polymers, but each of these polymers really has a different mode of action. For example, if I tell you the modified starch really promotes thixotropy more than viscosity, etc., we can go into it, but each of them has different mode of action or rate of effect on that mode of action we're looking at. So for each of these, we looked at them at a very, very low concentration. So these are percentages of the mass of cement. So 0.02% would be equivalent to 200 parts per million, which is very, very low if you are trying to promote segregation resistance, for example. And the reason we are using them is not so much to promote stability, but to promote robustness. The mixtures that we are using already is very, very stable. We also used PNS and polynaphthalene sulfonate. And yes, we still in Canada use a lot of PNS to make SCC, and we make very good SCC with it. And also polycarboxylate ether. So 2 types of superplasticizer, because we're also interested in the absence of any VMA, what is the difference between this mix in terms of robustness and the other one? And when you use a VMA or VA also, is there a difference between the 2 different type of superplasticizers? Okay, we selected one mixed design, and this is a mixed design that is targeted really for precast applications. So precast application, it could be structural applications, or it could be architectural type of applications. Like I said, the mix itself is very stable. It has quite a bit of cement, low water cement ratio, and aggregates are optimized, grading, etc. We are using very low dosages of VMAs to promote robustness. So we looked at the effect of variation of sand humidity by changing the water cement ratio of the mix from what it is was the surface saturated dry condition that gives us 0.37 to something that would simulate having a sand moisture content that is 1% minus, which is about 9 liters per cubic meter. So we are within the 10 that Nicola was talking about. And we also increased it by 1%, but that gives us a very low water cement ratio and moderate water cement ratio. So from 0.35 to 0.39, and this is how we did it. Excuse me. So we had our VMAs, 3 multiplied by 3 mixtures, 24 SCCs. We looked at many different properties. That was in the first part of the study. In the second part of the study, we selected a couple of these combinations. So one PNS plus a viscosity agent and a PC was another viscosity agent that gave us good results here. And then we looked at the variation of superplasticizer dosage. So the super dosage minus 10% plus 10%, simulating variabilities that we can get on batching of ACC. And again, we looked at workability, rheology, mechanical properties, and their variations. So I'm listing here some of the properties we looked at. So fresh properties, slump flow, air content, and their variation over time. T50, VSI, J-ring, surface settlement, rheology using concrete rheometer. And we also looked at thixotropy using a couple of test methods, portable vane and inclined plane, to allow us to look at the rate of increase in static yield stress with time. And also mechanical properties, both flexure and compressive strengths, up to 56 days. The test that I was mentioning that will allow us to evaluate structural buildup at rest, which is important in applications like form pressure, are the 3 tests that are below that you're probably not familiar with. So this is a portable vane where we have a vane inserted in concrete. After a certain period of test, we turn it using a torque meter and we determine the static yield stress necessary to break down the structure. And then we have the inclined plane where we can slump a concrete cylinder like this one over a plane, cover it. After a certain period of time, we can incline it, and once it starts to flow like an avalanche, we determine the static yield stress, and we can determine its variation over time. And then we have a very simple test, basically a 4x8 cylinder that is hollow on the bottom. We put it there, and after a certain period of time, we lift it and measure the variation of the slump flow in static at rest. Okay, so some of the examples, for example, if I'm looking at static yield stress, the test static stability, we like the surface settlement test, so we can look at the surface settlement and how it varies with variations of water cement ratio that are over here to simulate variations in sand humidity. So at SSD, we get, with this mix, with the PNS, no viscosity agent, we get fairly large surface settlement, about 0.65, 0.7%. And when you reduce the water cement ratio or sand humidity, you still have the same stability, but if you increase it, you lose stability and you get more surface settlement. More surface settlement, that means more internal bleeding, maybe external if you can measure it quick enough, and also more segregation. If I change my superplasticizer, or I add viscosity agents, you could see over here, everything is much more stable. So the surface settlement is lower. We like a maximum limit over here of 5.5%, so everything is lower, and there's very little variation also from going to the high water cement ratio from the SSD. Another example is to look at the yield stress at rests using a concrete rheometer. So if you have your target mix, the way it was designed at SSD at 0.37, you have the values. These are static yield stresses after 25 minutes of rest. This means it's very, very thixotropic. This is less thixotropic. But if we take one mix, for example, this one here, we see that the PCE and the mesocelo, the modified starch, we see something very, very robust. Otherwise, we see a big reduction in terms of static yield stress as you increase water or you increase sand humidity. So how do you read those graphs and to identify robustness? Well, we have two approaches. One of them is simply by saying, okay, what's the standard deviation of 3 measurements and what is the coefficient of variation? So a coefficient of variation that is 0, that means everything is constant. As it increases, that means the slope is increasing. So that's one approach. And here are the mixes. The mixtures, there was the PNS and the mixtures with the polycarboxylate. The first 2 columns here and here are the ones without any viscosity agents. And then you have the PS1, PS2, PS3, and PS1, the cellulosic and the modified starch. The reason we didn't use those was the PNS because there's an issue with compatibility. But then you look at the coefficient of variations, for example, in terms of air content, the huge variations. And you can see that in certain combination of superplasticizer viscosity agents, you reduce that variation a lot, and we start ranking them. So this would rank 1, this would rank 8 among 8s. We go down over here, 20 different properties. T50, gearing, static yield stress using the cones, variation of air content over 45 minutes, slump flow, etc., settlement. So we go through this. I'll give you a reference of the paper where you can find all this information later on. But this is how we looked at the ranking of different mixtures using all kind of test methods for the different mixture combinations. So mechanical properties, and how they also vary, the coefficient of variations. Usually mechanical property, the coefficient of variations are less than others. So the fresh properties, I would say, are much more sensitive to change in sand humidity than the mechanical properties that we are measuring between 0.35 and 0.39. Alright, so if you look at all the rankings, so you get the sum of ranks going all the way from, say, 27 to 71 for the different combinations. And then you can derive over here a normalized sum of ranks, which is basically the maximum sum of ranks for any given test of all of them, say 71 minus any given test, divided by the range of maximum plus minimum. And the normalized sum of ranks that is the highest will give you the best ranking. That means of all the 20 different properties that we measured, the one that is less sensitive, that is the most robust, would be the mix with the PNS and PS2. PS2, remember, is diatom gum that has a coarser grind of 75. Followed by the PNS with whaling gum that is coarser. Followed by PNS with the diatom gum that is finer. And down the list. Very surprising that the concrete, despite the fact that the concrete was 0.37, which is very, very stable, precast applications, made with polycarboxylate ether without any VMA, was the mixture that was the least robust. And the PNS was a little bit better, but not by much. But in principle, the mixtures that had PNS and a polysaccharide, VMAs, gave us the best robustness. So we divided that for further evaluation in the future into different categories in terms of robustness. Categories 1, 2, 3, and 4, depending on the normalized sum of ranks, to be in the very high robustness category, high robustness, medium, and low, and then you have the different mixes. So for the continuity of the study, which was to evaluate the effect of superplasticizer, we picked up 2 of these mixtures. We picked up mixture this one, number 2, and number 4, which were in the high, but not very high, but not moderate. And we wanted to see what would be the impact of adding 10% superplasticizer or subtracting on those properties. And this was done, among others, to also look at the methodology. Let's see. So we looked at 2 mixtures, PNS polycarboxylate, and we did the coefficient of variation that I showed you before, but also we looked at another approach, and that's the approach where we measure the compressive strengths at the surface saturated dry at the right dosage, and we measure it, for example, this is an example of compressive strengths at early age, 7 days, with more super and less super, and we determine what is the strength. But to look at the robustness, we had also to come up with what would be the minimum target for a strength compared to, we designed the mix for this. This is our mix, intended mix. So what would be the maximum variation from a minimum limit? So if we say, for example, at 7 days, I'd like to have 30 megapascal, so this would be 33 megapascal, or 32 megapascal, this would be 5% from the minimum. So we had minimum for all mechanical properties. Slump flow had to have a minimum value, for example, 600, and the J-ring also had to have a minimum value. So as you are adding more superplasticizer, you have some deviation from the maximum value, and then as you're reducing superplasticizer, you have a deviation from the minimum target, and we develop a ratio of this B divided by A, and we call that acceptance rate. So we'd like to know what is the acceptance rate for the variability of superplasticizer vis-a-vis the lowest limit, and if the acceptance rate is 100%, that means if I reduce my super by 10% or increase it by 10%, within that range, all my SCC mixtures meet that characteristic. Acceptance rate is 100%. So I'll show you an example. This is an acceptance rate for a settlement, so we have a maximum value instead of minimum value. And then here we had maximum values for our rheology. So here if I have a slump flow, and you measure with the superplasticizer your slump flow to be 610, and your minimum target value in this case is 592, which works well in inches. So you have a minimum of 3%. Increase the super, you get higher slump flow. You reduce the super, you get lower slump flow. And if you compare the rate of acceptance, you see that the rate of acceptance is about 50%. That means within a range of plus or minus 10%, I have 50% of my mixes only that can meet that rate of acceptance. Whereas over here in another type of mixture, PNS plus PS3, in terms of static yield stress, minus 10%, no variation, plus 10%, all of them meet the target. I'm within 100% all the time, and I can say that this concrete is very robust. Alright, so what we did is we looked at the rate of acceptances of the different properties that we evaluated, and they are listed over here for both mixtures, the PNS plus the Wayland gum, and the polycarboxylate plus the diatom gum. And these are the values we just looked at, but the rate of acceptance are here. And we wanted to compare if the rate of acceptance approach as a methodology would give us the same ranking, if you would, with the coefficient of variation that we also looked at. And if we look at all different properties we looked at, basically both of them tell us that if you're using coefficient of variation approach to determine robustness or rate of acceptance, both of them gave us basically the same type of ranking. So very quickly, and here I'm going to really hopefully whet your appetite to go and consult the paper, because there's a lot of statistical approach involved here, but we wanted to see, are there a set of test methods on the fresh and hardened properties that would give us the same kind of ranking as looking at 20 different properties. So these are the properties we're looking at in our study. Fresh properties, rheology, workability, their retention over time, and mechanical properties. And then looking at the Kendall's coefficient of concordance, which is a statistical approach, we were able to reduce the 20 to 10. That will give us also a very similar evaluation between the different chemical admixtures and their effect on robustness. And then also we applied another statistical approach, Spearman ranking. So you go from 20 to 11, and if you really have to for preliminary studies, you can even go to 3. So if you evaluate the surface settlement of your concrete, you evaluate the static yield stress of your concrete, which is also stability, and the 28-day strength. Of course, the slump flow is there as well, because that's the first target. Those tests will give you a good indication of the robustness that your chemical admixtures are providing for you. If you'd like to get more information on this study and all of the data you'd like to study them, It was published in 2011, ACI Materials Journal in volume 108. All right, I'm going to skip over this, but this is the ranking and how these three tests provide us with the concordance. The highest, the closer you are to one, that means the closer you are with concordance of the ranking had you run all different 20 tests. So I go to conclusions. From what we've shown today, we can say that SCC mixtures that are already stable but are made with PNS could be more robust than those made with polycarboxylate ethers. And the incorporation of VMA does enhance robustness. And again, I'd like to underline the VMA was used at very low dosage to enhance robustness and not so much stability because the mixtures were already stable. Those concretes made with polysaccharide viscosity enhancing agents exhibited greater robustness than those made with either the modified starch or the cellulosic base admixture, the HPMC. And either coefficient of variation approach or the rate of acceptance approach could be used to determine the robustness of the concrete. And then using the statistical approach for ranking different rankings, we could say that instead of going with a full-fledged study on fresh properties and mechanical properties, if you want to convince yourself that your concrete is stable, for accepting the concrete mix or the admixtures that go with it, or you can look at air volume, jarring, surface settlement, static yield stress, as well as mechanical properties. And if you really want to go from production point of view to look at robustness of your mix, then you can look at those three properties that are presented over here that will give you a much simpler, probably cheaper quality assurance, quality control testing. With that, I thank you for your attention. Peter.
I noticed that in one of your slides, at the very beginning you were comparing the effect of water content, and then at the very end of your presentation you was looking at the variation with Superplasticizer dosage. And you mentioned that in terms of robustness, the mechanical properties, at least based on compressive strength, wasn't necessarily affected when you vary the water dosage. Could you comment a little bit more on that in comparison to when you changed the Superplasticizer dosage?
Yeah, if you look at the coefficient of variation, for example, on any rheological property, they were very, very sensitive. Again, we are dealing with concrete that goes from a water-cement ratio point of view from 0.35 to 0.39. So your fresh properties would be very affected. In some cases, for example, you are not getting self-consolidation. You might get blockage in the jarring. Other cases, on the extreme side, you might get bleeding and segregation. But in terms of mechanical properties, because the window is so little, when you are measuring your 7, 28, 56-day mechanical properties, the variations were not that high.
But with the Superplasticizer dosages, it seemed as if it was more sensitive in terms
At 7 days, you're right. One of the graphs that was very steep was the 7-day compressive strength. At 7 days, if you are putting a lot of super, you're delaying setting and what have you. Yes.
Thank you.
Yes.
I just want to know the reason for using 10% variation in the Superplasticizer and 1% in the moisture. Is that related to the tolerances of the batch plants, or what's the source of these percentages?
Okay, the question is why do we choose plus and minus 1% on changes of humidity of the sand versus 10% on the super? These are within, if you look at many recommendations, you can even look at some of the reports from NCHRP, etc. But these are within production variations. For example, if you're using 900 kilogram per cubic meter of sand and you're changing that plus or minus 1% humidity, that means it's plus or minus 9 liters of overestimation or underestimation of water. And this is what Dr. Rousset was talking about, that within plus or minus 10 liters, you know. And the superplasticizer, if you're using a superplasticizer, say at 0.6, 0.5 liters per cubic meter, so you're looking at about plus or minus half a liter, which is within the precision, if you would.
Okay, thank you.
Could make it a lot higher, but we want our SCC mixtures to be better, tighter control, and that's what they need.
In trying to further understand your conclusion that the PNS seem to be a bit more robust than the PCE, is it perhaps because at a given yield stress, same water cement ratio, the PNS is giving us a higher viscosity than the PCE in your particular mixtures? I'm just trying to further understand why that's the case.
Actually, the polycarboxylate we were using gives you inherent viscosity. And you know that. That's how you design it, right? So it takes care of the stability issues. But the variability, I mean, as you know, the response with PNS is pretty linear. So you add more, you have lower yield stress, higher slump flow, you add a little bit more, it's pretty linear. But with polycarboxylate, it's not linear. It's linear initially, but it goes exponentially, and it goes back linear. But that exponentially is what throws us off. And obviously we are within that range. That plus or minus 10% are really throwing us off, or plus or minus water content that makes them more dispersed or less dispersed is throwing us off. But we've seen this in many studies, by the way. This is not the first time. We've done a lot of work using PNS and different type of pieces. And in the industrial chair, we have 2 PhD theses looking at the effect of admixtures and combinations on rheology of flowable concrete with that. And it's always, we see this with the polycarboxylate, you get the stability, but in terms of robustness, they're more sensitive. It does not have to be related to viscosity, because some of them have higher viscosity, some of them have lower. But you're right, as you add more PNS, for example, that can reduce yield stress, but also can increase your viscosity.
Thank you very much again, Kamal.